Hello everyone. So, let us look at the wave equation, or rather from wave equation to how the field equation looks like. So, in the last lecture we looked at how we can understand light propagation and how one can confine and how the light actually gets decayed, right. So, outside the waveguide structure. So, now we need to put a proper mathematics around this this understanding of light decay, that is a evanescent field, and the oscillating field inside. So, we need to look at the wave equation for that and find solutions to the structure that we have using Maxwell's equation. So, let's dive in. So, a wave equation could be approached by looking at different components that we have in the system. So, we have y, x and z. So, we will have field Ex, Ey, these are all possible fields for E, and you will have Hx, Hy and Hz. So, basically a common approach to find these fields is to solve the wave equation with a boundary condition, right. So, let us look at a linear isotropic waveguide. Right. So, linear isotropic is very important to understand, because this has implication on the permittivity. So, we want to take this as a isotropic medium. So, your dielectric constant is independent, spatially dependent, right. So, there are two laws we are going to the two Gauss law we are going to use for E and H, and we can write that taking those two Gauss law, we can write this del dot E be equal to minus del epsilon times E, and del dot H is going to be 0. Right. So, del dot E will not vanish in general, okay, because epsilon x y is spatially dependent, all right. So, that is something we should keep in mind. So, now let us use the Maxwell. We will have something of this kind. This is and for H field so, this is what we have once you apply the Maxwell into this, right. So, there are three components here. So, Ex, Ey and Ez for the electric field. They are generally coupled together, right, because your delta epsilon is non-zero, right, in a waveguide series. So, for the same reason Hx, Hy and Hez are also coupled, right. So, all these components are coupled, as I mentioned, right, and this as well. So, one could then that is the vector characteristic of these mode fields in a waveguide are strongly dependent on the geometry and the refractive index profile of your waveguide. The reason for that is epsilon x y, right. It strongly depends on the dielectric constant, how it is represented in the structure. So, for a TE mode, right, in case of a TE mode, let us say we have delta epsilon perpendicular to E, so that you are equal to 0. So, each component of the electric field of a TE mode satisfies a homogeneous scalar differential equation. Okay. So, the magnetic field component of TE modes are still coupled. So, they are all coupled as well. All right. So, with this let us look at a very simple understanding of a step index waveguide. So, wave equation for a step index profile. So, step index is something that we already saw, where you have n2 and n1. So, this is a function of x. So, you have two different refractive indices or three different refractive indices, depends on how you want to do this. All right. So, now we can write a homogeneous wave equation, right, separately for this different regions, right. So, you will have epsilon 1 here, epsilon 2 here, and for all practical purpose you could also have n3 here if we want. All right. So, we can put it little bit lower if you want. So, we can write this there because the constant epsilon becomes 0 here. So, within each region. So, within a region delta epsilon is 0 within each region, right, but then between the region it is not. So, if you look at the whole structure altogether, your delta epsilon is non-zero, but inside the medium a delta epsilon is 0 because it is uniform medium. So, assuming E and H are harmonic guided waves, then we can write the longitudinal component, right, as dou square Ez or dou x squared. So, this is nothing but longitudinal field component plus dou squared Ez by dou y squared plus k I squared minus beta squared 2. So, k I represent whichever medium you are in, whether in n1 or n2 or n3. So, similarly we can do it for H field as well. So, dou squared H z by dou x squared plus dou squared H by dou y squared plus k I squared minus beta squared to H z is equal to 0. So, your x y field, right, is where you have your fields, and that is why we do it this way, and here k I squared is nothing but omega squared mu naught epsilon I, all right, which is nothing but n I squared omega squared okay c squared, right. It is a constant within each region, right. So, if you are talking about region n1, and this is a constant. If it is n2, this is a constant based on the refractive index. So, this homogeneous equation is same as the same form, right, written for each of these field components. You can do it for x, y, and then hx and hy. And it is not necessary to solve for each and every component. Okay, it is important. It is not necessary to solve for all field component. So, it is not required. It is not necessary to solve for all the field components that we have. It is good enough if we solve or if we find z of h and h of z. So, this is good enough. By doing this, we can actually expand and then find the other components. So, the mode field pattern can be obtained by solving just two equations. So, whatever we have here, we do not need to have the 6 equations that one can expand for the 3 components here, Ex, Ey, Ez and Hx, Xy and Hz. So, we do not have to do that. So, we can just keep it this way, where just 2 components are good enough in order to extract the other components. And how do we get that is by using the boundary condition, these interfaces, right, between the different regions we have. Based on that we should be able to do that. So let us look at how one can use this approach to find the solution of this electric field or magnetic field in a very simple planar waveguide. Let us look at a very simple planar waveguide here. We have a waveguide that has refractive index n1 here, n3 and n2. So light is propagating through this, right, and the coordinate system is similar to what we have been discussing so far. So the direction of propagation is z, and we have field in x and y direction. So here n1 is greater than n2 and n3. So that is something given. So we call this as a simple slab waveguide, right. So for this let us look at both TE and TM. So you will have TE mode and you will also have TM mode. So we could consider d over dou y is 0 because the refractive index profile change across y direction is nil, right. There is no change in the refractive index along y. So your dou over dou y, right, is going to be 0. So there is no change there. So this will actually reduce the complexity that we are going to have here, right. So this is very useful, starting up with a very simple planar waveguide. So for TE wave, let us look at how the TE is going to be. For a TE planar wave, in a planar waveguide. So let me where Ez will be 0, right. So such that the form relation, right, the relation here for transverse component to the longitudinal component is that Ex will be equal to Hy, which is 0 because dou Hz over dou y is 0. So your dou Hy over dou y is 0, right, because field is continuous, and your Ex and Hy will be 0 as well here, right. So this is the implication here. So the only non-vanishing part or field are Hx, Ey and Hz. So look at it. So this is something we already noted, right. So the dou over dou y is going to be 0. So dou Hy over dou y is 0 in this case, and that will result in Ex and Hy being 0, alright. So because of this implication, the only non-vanishing part we have is Hx, Ey and Hz. Okay. So because there is only one non-vanishing electric field, right. So there is only one non-vanishing E field, right, and that is your Ey, and this becomes much more simplified like this, right, and your k here is omega square mu naught into epsilon over x, right. And you can get from this, you can get our Hx equal to minus beta over omega mu naught where Ey, and Hz could be 1 by I omega mu naught dou Ey over d by x. So now we can do a similar approach for Tm waveguides as well, right. So Tm mode as well. So in terms of Tm, your Hz field is 0, right. This is only for planar waveguide, right. In a planar waveguide, your Hz is 0, and since your field is 0, this implies Hx and Ey are also going to 0. And now since you have only one H field that is non-vanishing, so here non-vanishing fields are Ex, Hy and Ez. So now we can write your H field as right. So this is actually your H field, and now from this H field we know we can get Ex field, which is beta omega epsilon and Hy, and then we can also get Ez field, which is, so you can apply this into our earlier equations that we saw. We should be able to get these fields done. So now having these fields defined, right, so this is how they are going to look, right, but we have to still find the modal solution here, how the fields are going to look like. So this is just the wave equation, right. We don't know the solutions for this, right. So we know we have formulated the wave equation, the wave equation, but we need to find a solution to this wave equation. So let's look at how the solution could be. All right. So the solution to the wave equation. So let's assume that this is how the solution will be, right. So for a TE field, right. Unit vector here, so field is along x e to the power I beta z minus omega t. So this is very simple form, right. So when you substitute this into our wave equation here, so what is the wave equation? Dou squared Ey by dou x square plus Ki I square minus beta square Ey equals to 0. So we need to substitute this, right, substitute this in the wave equation, and this we can solve this the second order differential equation, and your solution for this, right, will be equal to e to the power plus or minus Ix root of Ki squared minus beta squared. So this is how your field is going to look like, and the solutions are going to be sinusoidal in nature, that you can see from here. So it will be sinusoidal, right, depending on the magnitude of k, right. So let's look at the nature of this solution. So we have to look at this factor and Ki squared, whether it is greater than beta square or less than beta square. So these two are two possibilities. So when Ki squared is greater than beta square, this will result in the sinusoidal solution, and if Ki square is less than beta, this will result in exponential result. All right. So if a mode or if a solution, right, needs to be propagated through a waveguide, we call it that guided mode. If you want to have a mode that is guided, right, the cladding region should be exponential. That means we saw earlier, right. So, something like this. So, in the cladding region you want the solution to be having exponential solution, while in the core region it should have sinusoidal solution. All right. So, how to achieve that? Right. So, we have this, let us say this is N1 and N2 and N3, let us say, right. So, in this case you want for a guided mode, you want the beta that is propagating through this should be greater than K2 and K3, right. So, this is what you want for an exponential solution, but now beta should be less than K1, right, to have a sinusoidal solution. All right. So, this is the condition that you want to have when you are having such a a waveguide structure, right. So, this is exponential half, this is sinusoidal. All right. So, let us look at the field component. What is the general form that you can define for these different regions? Okay. So, let us take a simple waveguide structure here. And we have a core and we have clad, right. So, we define a simple core here. This is x and let us say this is y. So, we are going to look at how the field is going to look like, right. So, in the core your field is be something of this kind, while in the cladding let us say some thickness, right. So, you have some thickness d and here this is 0 1 d and so on, and here the field will look something like e to the power minus alpha x. So, you can see the oscillating field is at the center and while the field outside are decaying. All right. So, we could go back to our earlier discussion in the last class, I believe, where we looked at the phase matching condition, right, in order to achieve the similar kind of results here. So, here again from the detailed wave equation and solving the wave equation, we also arrive at the same. So, all these constant a, b, c, d, right. So, these are all constants, right, that will determine the oscillation strength and so on. All right. So, the boundary condition is definitely useful in understanding this, and based on this you can find both for TE modes and also for TM modes in order to arrive at the same kind of solution that we had. All right. So, this is rather important to understand how we achieved oscillating solution, or what are all the conditions to achieve oscillating solution. You can keep a close eye on the approach here. This is coming from assumption that E field is only in x y direction, right. Okay. So, each field is distributed when the light is when the field is in the x y plane, right, and it is propagating along z plane, right. So, that is a reasonable assumption that we have made and holds good in many circumstances. All right. So, with that we have come to an end to this particular topic in finding the field nature right. So, how the field is going to be inside the waveguide and outside the waveguide. We had two different approaches, and here we looked at the wave equation and then solving the wave equation, and we were able to achieve it. And we could also do a similar kind of approach by just simply looking at the wave vectors and how the phase matching happens, and based on that we should be able to do that. In the next class we will look at some of the important parameters that we use to characterize the waveguides. All right. So, with that, thank you very much for listening.